Vanderbilt University and the Institute for Software Integrated Systems present RegTrack, our one-stop solution for relative GPS tracking. The motivation behind our research stems from the fact that a large number of mobile sensor applications require precise knowledge of only the relative locations of the nodes. While GPS is becoming a standard for outdoor localization, it provides absolute coordinates that may be vastly out of the accuracy range of a given application. As such, we started from the ground up, building a new system that enables a network of cooperating GPS receivers to share their raw satellite data, such that any given receiver is able to accurately track the 3D position vectors of any other receiver in its own relative coordinate system, that is to say, using itself as a reference. We use a threefold approach to achieve this, consisting of devising new error models that incorporate measurement errors specific to localization in the multiple receiver case and correcting for these errors, creating a set of new observation models which allow us to use highly accurate accumulated phase measurements of the GPS carrier signal with no explicit reference satellite or node to determine the change in range between a satellite and receiver pair through time, and using these error corrections and observation models to implement a pairwise tracking function in which each individual receiver node can map the pairwise 3D relative tracking vectors to any number of other nodes in its vicinity without needing to know its own position to any particular degree of accuracy. We decided to call our system RegTrack and implemented it on a series of Android smartphones networked via a wireless router and connected via a custom Bluetooth chip to a MuBlox LEA6T series commercial-grade GPS receiver, since the phones themselves did not provide the required satellite data externally. As a proof of concept, we carried out several experiments to test the limits of our system, but perhaps the easiest one to visualize is a driving experiment, which we'll show here. In this demo, we attached 3 of these GPS nodes to the top of a car in this parking lot. We also set up a stationary node like so to enable us to map the ground truth of the 3 roving nodes as they drive around in different speeds and different GPS environments. On this Google Map visualization of the results of the experiment, the 3 blue circles indicate the nodes on the roof of the car, and the red circle indicates the stationary node, whose point of view we are showing in this video. In other words, the locations of the traveling nodes are what the stationary node is calculating them to be. Also note that since this is a tracking algorithm, we had to manually initialize the relative locations of the 3 nodes before the experiment started. So to begin, the car started by driving out of the parking lot and turning onto this narrow alleyway with buildings on either side, ranging from 2 to 4 stories tall, and quite a few trees, as you can see here in the Google Earth imagery. The important thing to note here is the constant geometry of the nodes relative to one another, given the high multipath environment and fairly narrow view of the sky that's available to the nodes. After turning out of the alleyway, we drive on suburban roads for a while, which is what you see here. Watch here in just a second. You'll be able to clearly see the car navigate a lane change. Right here. And then we change back into the right lane. The ability to clearly discriminate this driving feature in and of itself shows a marked improvement over standard GPS positioning. At this point, we change to a single-track view so you can see the tracking history of the car more clearly. Note that the node we're showing tracking data for is the one directly above the driver's side door, so the track should always appear fairly close to the left side of the lane. At this point, we've been driving through both obstructed and multipath-rich alleyways, as well as suburban roads for about 5 minutes, and we've covered roughly 2 kilometers of road. We then turned onto an interstate highway, which is what you're seeing here, driving about 70 miles per hour. You can see that the track is remarkably close to where we expect it to be. And also remember that the track you're seeing is being computed by and relative to the stationary node back in the parking lot, which is over 3 kilometers away at this point. So in addition to the technique being accurate at close proximities, it scales well to longer and longer baselines. After driving on the interstate for about 10 more minutes, we do encounter a small problem, namely that we go under a large overpass that causes us to lose locks on the satellite signals while we're changing directions for just long enough that our accuracy degrades and the track appears a good 3 or 4 meters to the left and down from where it should be. At this point, we have exited the interstate and are making our way back to the starting point on more suburban roads at about 30 miles per hour. Notice that the offset error we accrued at the end of the interstate portion is still present, but it doesn't appear to have grown in magnitude. Without this error, we'd be turning in right where we should be. You can see we pull in, drive around the parking lot, and end up about 2.5 meters from where we started and where we are in real life. Keep in mind that we just finished driving for over 20 minutes and covered over 12 kilometers, accumulating just 2 meters of error using tracking alone under moderate to severe GPS conditions. In the future, we hope to solve the missing pieces of initialization and recalibration within the method itself to provide a truly ubiquitous outdoor localization service for high-precision applications. For now, we're just excited about the results of this first phase of our project, and it's been our pleasure to share with you our novel relative GPS tracking technique, RegTrack.